Okay, we're going to work another Taylor polynomial example problem. Given this function here, we want to find the second degree Taylor polynomial centered at 4, and then use Taylor's inequality to estimate the largest possible error that we can have using that Taylor polynomial to estimate the value of the function if we're restricting the input x values into the Taylor polynomial to be over this range here. And then we're going to graph the actual error value as a function of x. So that's going to be the function subtracted, or the Taylor polynomial subtracted from the actual function, and compare that to what we got with Taylor's inequality. All right, so we start by going through the same procedure that we would use to get the actual Taylor series of this function. So we make two columns. On the left is the function and its derivative, so x to the minus 1/2, which is 1 over root x. Okay, now let's take some derivatives. So we've got minus 1/2 x to the minus 1/2 minus 1 is minus 3/2. That's okay. Second derivative is, so minus 3/2 times minus 1/2 is 3/4. X to the minus 3/2 minus 1 minus 3/2 minus 2 over 2 is minus 5/2. Okay, now this is all of the derivatives we're going to need to, because n corresponds to, we're not summing the first two terms necessarily of the Taylor series of this function. That could be the case, that's what it turns out to be. But specifically, this is more specifying the order of the Taylor polynomial. It's going to be, we're going to go up to the x squared term in the Taylor polynomial, no matter how many terms that ends up summing. Okay, so this would be enough to get to that second order term. However, we want to go one derivative past this, because we're going to be using Taylor's inequality. So 3/4 times minus 5/2 is minus 15/8. X to the minus 7/2 Okay, so now we come to the right column and plug in the center point to each one of these. So the center point is 4, 1/2, okay, so this is x times root x, right? You could take an x squared, you could take out an x, so 2 times 4 is 8. 8 times root 4, so this is minus 1 over 16. All right. So here we've got x squared root x. So 16 times 4 is, so it's 4 times 16. 16 times 4 is 64. Times 2, it's 128. So 128 and then 3. Let's go ahead and plug this in just to make sure I'm not. So 4 to the 5th, 128, 3 divided by that. Okay, so now 4 to the 7th, 128 times 8 minus 15 divided by that, minus 15 over 1024. All right. Okay, so now we don't need to look for any patterns or anything because we're just going to write out the first three terms. So we know that in the Taylor polynomial, each coefficient is the nth derivative evaluated at the center point over n factorial. So the c sub n's here are, so this is c sub 0. So like this is the nth derivatives evaluated at a. So we need to divide these by n factorial. Well, this divided by 0 factorial is just 1/2. This divided by 1 factorial is just minus 1/16. This divided by 2 factorial is, so 128 times 2 is 256. So, okay, and that's all we need for the Taylor polynomial. So we've got t sub 2 is, so 1/2 times x minus a to the 0, and then minus the coefficient here times x minus a is 4 to the first power, and then the c sub 2 times x minus a squared. So yeah, there's the second order. That's t sub 2. All right, now this is approximately equal to the function, right? That's it. There you go. In particular, if you stay near the center point, near 4, then if whatever x you plug in here, if you're near 4, it's going to be close to if you plugged in that same value here. That's the idea. Okay. So now we want to use Taylor's inequality to figure out what is the maximum possible error that we can get using this to approximate the function. So the error meaning the difference between the value that you get out of the Taylor polynomial from the value you would get if you plug that same x value into the function. What's the maximum possible error you could get, assuming that we're restricting the inputs that we can, the x values that we're going to input to this range here. You can see it's plus or minus 0.5 from the center. Okay, so how do you use Taylor's inequality? Well, it's all about, the Taylor's inequality is giving us the r sub n. The absolute value of the r sub n, it's not giving us the r sub n, it's giving us a upper limit on it. That's it. That's the goal. If we have the upper limit on the r sub n, then we have the answer to what we're looking for. So if you look here, we choose an n. We've chose n is equal to 2. Okay, we choose a is 4. We chose d here. D is, it's 0.5, right? It's x. The absolute value of the x value minus the center point is going to be at most 0.5. So all we need to get this filled out is we need the capital M. Taylor's inequality is all about finding this capital M, and capital M is based on this. This is what you use. This is what capital M means. So it's we need the n plus 1th derivative. There it is, minus 15 over 8 times the square root of x to the 7th. We can simplify this, so it's 8. This is x squared times x squared times x squared times x. So x cubed root x. There's the third derivative. So okay, now we're looking at that's in the n plus 1th derivative. If we take the absolute value of this, we get but we still want to leave the absolute value because x could be we could input a negative x, right? Okay, now what we're looking for is there some value m for absolute value of x minus 4 is less than or equal to, we can see it's 0.5, which this is just saying that for x in this range here, that's what this is saying. These two mean the exact same thing. Okay, is there some capital M to where no matter what x you plug in this range or in this range, that value is greater than or equal to all of the other values of this function here, the absolute value of the third derivative of x? Well, okay, that we can potentially graph this if we need to. We could actually go get the graph, but we could also just think about, well, all right, if we plugged in 4.5 or 3.5, it could be the case that like we're thinking about this as a function, right? If we graphed this, just look at the graph over going from 3.5 to 4.5, just look at the graph, whatever it's doing. What's the largest value? Is it at the endpoints? Okay, there you go. That's capital M. Is it? Oh, it's right here. There's capital M. That's it. It's that simple. So what we can see is that it works out here to where if the smallest value, the smallest x value is going to make this the largest for this case here. Right? We could have removed the absolute value because this can't be negative for the case that we're considering. Like once we add this restriction, we could just remove the absolute value here. So it's going to be when 3.5 is going to be that value. Okay, so we can say that the f triple prime, this is less than or equal to, and we just plug, so 3.5 cubed times the square root of 3.5 times 8, 15 divided by that, 0.023376. For there we go, right? This is 100% true. There's no other x value you could plug in this range here. Plug into f triple prime of x, the absolute value of that, and get something that's bigger than this. Okay, so this is M. We've got M. So now we have what we need. This upper limit on the absolute value of the error. So we're going to plug in n is equal to 2. What we're trying to get is we're trying to get, so the Taylor series of the function, that's the Taylor, this is equal to the function, right? This is equal to t sub 2 of x plus r sub 2 of x. We're trying to get an estimation of the size of r sub 2. So we're going to plug 2 in here. Okay, so the absolute value of r sub 2 of x is less than or equal to, so it was n plus 1 factorial, and then capital N up, or capital M up here, and then it was times the absolute value of x minus the center point to the n plus 1. Okay, now this is equal to, so that divided by 3 factorial is 6.003896. Okay, so that's the upper bound on this r sub 2, okay, which is the amount that we're off from the actual function, the infinite sum, but it depends on the x that we pick. Now you might say, well, didn't we already pick an x? We picked x is equal to 3.5. No, that was something independent of where we're at now. That was just to find what m was. We could pick a different x here. I mean, we just found m. That's all we did here. And we just saw that m was at x equal to 3.5, but now we're done with that. Here's the absolute value of r sub 2 of x. Here it is. So what we want to do is, if we're trying to answer the question, what's the, for whatever x we plug into t sub 2 here, that's within this range, if we plug in any x, what's the largest the off we could possibly be from the actual function? What's the largest off we could possibly be? Okay, well, what x would that be here? Between 3.5 and 4.5, what x would that be? Well, okay, this is just going to be at the endpoints once again. We could choose any of the endpoints. The farthest we could go away from 4 is 0.5, so we'll just replace x minus 4 with 0.5. Okay, so if we do that, we get, so 0.5 cubed, and then times this, 0.000487. And there it is. Okay, now you might be wondering, well, why didn't we just plugged in 3 or 4.5 or 3.5 into here? No. This is, we're answering the original question. The r sub 2, okay? Here's r sub 2. If you take any x value and you plug it into the function and you plug it into the Taylor polynomial and you plug it into the r sub 2, any x value, you could pick x is equal to 3.2, whatever, or no, 3.7, 3.8, and plug it in. That's what r sub 2 is. The absolute value of r sub 2 is. It's that error. This isn't a specific number. It depends on the x you choose. We're saying that this value here, which represents the error, the absolute value of the error, no matter what x you put, as long as it's within that interval from 3.5 to 4.5, no matter what x you put, it's going to be less than this. That is the answer to the question we were trying to answer. Okay, so now let's graph the actual r sub 2 of x. So how do we do that? Well, we know that, so the absolute value of r sub 2 of x, that's equal to the absolute value of the function minus the Taylor polynomial. So that's 1/2 plus 1/16, distribute that minus right? We can graph this. Now you might be wondering, well, why would we do the Taylor's inequality? Why wouldn't we just use this to get the error? Yeah, you might do that. These problems are just to illustrate Taylor's inequality and Taylor polynomials. It depends. Maybe you don't actually have the function, or maybe it's difficult to get the graph of this graph. It just depends. Okay, so let's graph this. Okay, here's the absolute value of r sub 2 of x. We're going from, so, okay, here's 3.5, here's 4.5. So it looks like this side's a little bit higher. So this is 0.00025. So maybe 0.0003, 0.0035, something like that. And we got 0.000487, so not bad, pretty close.